the first thing it says is to draw the correct Lewis structure for phosphorus acid, right? H3PO3, below identified steric number, electron geometry, molecular geometry, the hybridization of the central atom, and its polarity. And the reason why I had all that there is, of course, because I'm going to continue testing you on Lewis structures and geometries and stuff like that. But also the other reason why too is because when you look at this acid right here, it looks like it has three protons right there, but when you draw its Lewis structure, you can see that it doesn't actually have three protons that are available for a for a donation as a Bronsted-Lowry acid, right? So so the first question, right, of course, is to draw the Lewis structure. So it's quite easy actually. Always have the phosphorus in the center, right? And then the part that's easy is this part here, because this is just like phosphoric acid, right? Phosphoric acid and phosphorus acid have those two the same, right? Where it changes is the fact that phosphorus acid only has three protons on it, so sorry, three oxygens on it. So instead of four, so that we can complete the outer shell of phosphorus, we actually have to have five bonds to it, and the only way we can get five bonds to it is by drawing it like this, right? Drawing it like that. So that's the correct Lewis structure for phosphorus acid, okay? And that's very different because phosphoric acid, the one that's more common, which is the strong acid, actually has this proton connected to the one of the oxygens, right? And then the other one has a double bonded oxygen there. So that's why this one is slightly different. It's almost a trick question. I asked several people before I gave you this, is what is the Lewis structure for phosphorus acid, and how many protons can be used as an acidic proton? And almost every single person I asked thought it was three, right? But in fact, it's only two. Okay, and the reason why it's only two is because the only protons that can be acidic protons are the two protons that are on the oxygens, right? Uh, the reason why that is because the phosphorus. So for something to be acidic, right, the thing that the proton is attached to has to have a different electronegativity, right? It turns out that both phosphorus and the hydrogen right here, where it's connected right there, both have the same electronegativity. So that alone says it can't be an acidic proton, right? But you already know for a fact that the electronegativity between oxygen and hydrogen are very different. They're off by like one. On a scale of 1 to 3, they're off by like one entire unit. So that's that in the general chemistry sense, right? In the general chemistry sense, the protons on the oxygens have a different electronegativity, and that's why they're the ones that are acidic. But in the even more, I guess, organic chemistry sense, things that are more acidic become more acidic because of resonance stabilization. For example, if there was a base that were to come over, like a hydroxide, came over and takes that proton right there, right? That there's a bond between the proton and the oxygen, and this bond would come down, right, and form a double bond there, and then make this bond from this double bond oxygen go there, and then you get a structure that looks like this. That looks like that, right? And now you have a negative charge right here, okay? And so on that oxygen right there. And so what we call this is called resonance stabilization, right? You can only do resonance stabilization if you have lone pairs, right? But a proton and a phosphorus doesn't have a lone pair to do that with. But oxygens have plenty of lone pairs, right? And so that's why they can do this thing called resonance stabilization. And the reason why I showed you this is because when it comes down to it, it loses one proton. You're like, so if it loses one proton, how does it become a negative charge? It becomes a negative charge because of this right here, this one single bonded three lone pair oxygen right there, right? So what I was looking for you to draw though, as the Lewis structure here, was that, right? And I was hoping that you draw it such that you had one hydrogen that was connected to the phosphorus, and then the other two were connected to oxygens, so that you could see that in fact, based on its Lewis structure, this is a diprotic acid, not a triprotic acid like most people would think. Now, if that were phosphoric acid, that would be different, right? Because on phosphoric acid, so let's just be clear about what's happening here. So that's phosphorus acid, right? Phosphoric acid looks like this. Right? That's phosphoric acid right there. And notice that every proton on phosphoric acid is connected to an oxygen, right? And that's the reason why phosphoric acid here is triprotic, and then phosphorus acid here is diprotic. Right, right.
Wait, why is it diprotic? Sorry, can you repeat that?
Phosphorus acid here is diprotic because it only has two protons that can be used as acidic protons,
Oh, okay.
right? Because these are the two protons that are attached to the oxygen right here. On the other hand, though, phosphoric acid, which is a strong acid, has all three of the protons attached to oxygens, right? So that's why all three of these can actually be used as acidic protons. Okay, so it's a very, very huge, very large misconception that phosphorus acid is triprotic because looking at it like just by its formula, doesn't it look a lot like phosphoric acid, right? I mean, everybody thinks that it's going to be triprotic because it looks a lot like phosphoric acid, but nope. In actuality, phosphorus acid is only diprotic, and you can see why it's diprotic, right? You've got to maintain 5 bonds around the phosphorus, right? But the only way to have 5 bonds after you draw a correct Lewis structure, right? After you draw the correct Lewis structure, is by having one of the protons actually attached to the phosphorus so that you can have a double bond with on the oxygens. You don't have to do that with the phosphoric acid because you already have 3 bonds from the 3 oxygens and a double bonded oxygen right there, right? So, and you'll see if you go through, and I'm not going to make you do this, but if you want to do this, go through the 6 steps, right, of making correct Lewis structures. And once you count up all of phosphorus's electrons, count up all the electrons that are available from the oxygens and the hydrogens, right, you're going to end up with a point where you have to make a double bond between something, and the only thing you can make a double bond with is an oxygen by itself, right? We won't go through that now. That was like months ago, but that's the reason why. Okay. And I'm talking to you about this now because we're about to jump into doing acid-base equilibrium with multiprotic acids or polyprotic acids, right? So I'll give you a name, right, or a formula, and you're going to have to figure out whether or not it's diprotic or triprotic, and most are pretty easy to figure out. It's just phosphorus acid is the one that's a little bit ambiguous, but it actually isn't ambiguous. It's clear when you draw out the Lewis structure that it's the way it is there. It's diprotic. Okay, so here's the answer that I was looking for right there. That was the answer for that. Okay, so looking at that next problem, right? The next question in the problem was what is a steric number? Its steric number is 4, right? And then it's let me get the pen working again. I wish there was an easier way to do this. All right, its steric number is 4, right? Because it has 1, 2, 3, 4 electron domains, right? And when you have a steric number of 4 with a steric number of 4 electron domains and no lone pairs, that means electron geometry and molecular geometry is going to be what? Tetrahedral. Right? Both are going to be tetrahedral. Okay? Now, if it had a lone pair, it'd be trigonal pyramidal, right? But it's not a lone pair. It's 4 bond groups with no lone pairs, so it's going to be tetrahedral. Okay? And then it's asking for the hybridization of the central atom. The central atom is phosphorus, and it has 4 electron domains on it. It's a steric number 4, so we're going to say that it is sp3 hybridized. And very lastly, what is its polarity? We can see that this side over here has a bunch of oxygens right here, or just this one big oxygen on this side, right? And on this side has a bunch of protons. So it's definitely polar. Okay. So that's everything from the first part of the question. We've already answered question A, right? We've already answered question A, and I actually want to erase something again so that I can use it as an example. I'm going to erase that. I'm going to erase that. Erase those arrows. There we go. Okay. You can tell that these acid-base equilibrium problems take a lot of paper. I mean, like space. Okay, so we already know it's diprotic for the reasons I explained a few minutes ago, right? And then, so the next question is, if you have a 25 mil sample of phosphorus acid and you titrated it with 0.102 molar sodium hydroxide, and it requires 23.3 mils of it to reach the endpoint, what is the concentration in molar of the phosphorus acid, right? So you should have done titration calculations back in Gen Chem 1, okay? So this is reaching back to your Gen Chem 1 days. But just in case you don't remember how to do a titration calculation, the first thing to do is to figure out how many moles there are of sodium hydroxide that actually made the phosphorus acid go to its endpoint, okay? The way you do that is you start out with the volume that you have, right, of the sodium hydroxide, and everything is always going to be in liters, so it's going to be 0.0233 liters of sodium hydroxide, right? Because remember, moles divided by liters is what molarity is, so that's why you got to make it liters, okay? And then you're going to convert that into moles by saying how many moles of the sodium hydroxide you had. Oops, didn't mean to do that. Let's go back here. There we go. And so it says right there that the concentration of the sodium hydroxide was 0.102. So that's going to be 0.102 moles of sodium hydroxide. And all that is over, how much is that over? It's going to be over 1 liter, right? Because that's what the unit is for molarity. 1 liter of NaOH, like so, okay? Which is great because now you can cancel out liters of sodium hydroxide and you're left with moles of sodium hydroxide. So how many moles of sodium hydroxide do we end up with here? It is, I believe, it's 2.38 times 10 to the negative 3 moles of NaOH. Okay? We're not done yet, though. We've got to figure out still what the concentration of the phosphorus acid is. How do we figure out the concentration of the phosphorus acid? We have to use the molar ratio, the stoichiometric ratio, right? And the reason why you needed to figure out what the balanced equation was in discussion is so that you knew what the stoichiometric ratio is. And so the balanced equation is this. You start out with H3PO3, right? And you add, that's always AQ. You add some water to it, which is liquid, right? And then what you get at the end is the sodium salt of it, which is Na2HPO3 plus 2 waters.
What
Go.
happened to the sodium hydroxide? Like, why isn't that in the?
Oh, just because I screwed up. That's why. I'm sorry. Let me fix that. This is supposed to be sodium hydroxide right here. My bad. There we go. Sorry. Good call. And there's 2 of those. And that's also AQ. There we go. Okay, now that should be the correct balanced equation. That should be the correct balanced equation. All right, so now that we have the correct balanced equation, we know that for every 1 mole of, go ahead. Don't forget that when you have a neutralization reaction, an acid plus a base makes what? Exactly, a salt and water.
A salt and water.
Yes, that's always true. A neutralization reaction always results in a salt and a water. Okay, so we can see in our completely balanced equation, now that I've corrected it twice, because I wrote it down in the wrong order. But anyway, we can see now that the corrected balanced equation is phosphorus acid plus 2 sodium hydroxides make you the sodium phosphorus and the 2 waters. Okay? What that means then is that we have 1 mole of sodium phosphate for every 2 moles of sodium hydroxide, right? That's what we're looking for. Okay? That's what we're looking for. Okay, that's what we're looking for. And so, knowing that, you can say then that 2.38 times 10 to the negative 3 moles of sodium hydroxide, right, can then be used in dimensional analysis to figure out how many moles there was of phosphorus acid. And so down here we have for every 2 moles of sodium hydroxide, like so, right? Which is good because now we can cancel out moles of sodium hydroxide. And then at the top, what do we put? What do we put at the top of that? What are we trying to get to? Of, yes, phosphorus acid. So that's 1 mole of phosphorus acid. Like that. See? So the reason why you needed a completely balanced chemical equation here, like Miss Dickens told you, right, in discussion, is because from the balanced equation, you know that for every 1 mole of phosphorus acid, which is in the top row right here of the dimensional analysis, there's 2 moles of sodium hydroxide down here at the bottom of the dimensional analysis, right? So awesomely enough, moles of sodium hydroxide cancel out, and you're left with what? Moles of phosphorus acid. Okay, moles of phosphorus acid. Yes, that's exactly what I got. That is correct. That is exactly what I got. Times 10 to the negative 3, right? Moles of phosphorus acid, right? But now that's just number of moles. We need to get that to concentration. How do we get that to concentration? Well, that was actually given to us in the problem right here. It is a 25 mil sample of phosphorus acid. So you see how you have to pull out 3 or 4 different numbers from that problem, right? So at the very beginning of the problem, it said there's 25 mils, and then concentration is always number of moles over liters, so you can divide all that by 0.025 liters, and that gives you the concentration you're looking for. Right? That'll give you the concentration you're looking for. And again, I put 0.025 liters instead of 25 milliliters because the formula for concentration, molarity, is what? Moles over liters, right? Not moles over milliliters, but moles over liters, right? I heard a wait. What's up?
Wait, can you remind me of something real quick? Why
What?
did you put 0.025 instead of 25? Sorry.
Because the concentration formula, molarity, right, is number of moles over liters,
Oh, yeah.
not number of moles over milliliters, right?
Yeah.
And I gave you the number of moles, sorry, I gave you the volume in milliliters, so you needed to convert it to liters, which at this point, though, you should be able to do in your head. No, it's okay. At this point, you should be able to do in your head because you're just moving the decimal point 3 places either way, right? You should be able to do that stuff in your head now. All right, so that gives us then the formula, that gives us then the concentration of H3PO3, right, to be, and someone check my math on this, 0.0476 molar. No, that's close enough. That's a rounding error. That's close enough. No, it's okay. No, I mean, you don't know unless I tell you that's a rounding error, right? Yeah, usually if you go out to that many decimal points, right? Like to like the thousands place or even the tens of thousands place, if it's off by one, that's okay. You're okay about that. You don't have to worry about that so much. I messed up. That's why I'm erasing it right now. Yeah, yeah. No, it's okay. I just miswrote, so I was trying to erase it so that it wasn't so messy. Instead of crossing it out, there we go. So it should be molar H3PO3. That's what we should be ending up with. Okay. Okay. Good. 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 Right. So there's the answer to the B right there. What is the concentration in molar? Right. What is the concentration in molar of the phosphorus acid? Okay. And so that was B. So I guess I should write in here which is which. Um, so here's A right here, right? And I erased it, but it is diprotic, right? And then the answer to B is this one. There. Okay. So now we can move on to C, right? Now we can move on to C. The original solution from part B has a pH of 1.59, right? Calculate the percent ionization for just Ka1, right? And the reason why you're doing this is because we know that the very first proton, Ka1, is going to be much larger than Ka2. So that's the one that's going to be the effective proton we're losing, right? And then for the third proton, it doesn't get lost at all because it's not even acidic, okay? Luckily for us, we were given this, the pH of 1.59. What can we use? What can we do with that will give us something that's helpful? Since it's given us the pH, you know that the negative log of the hydronium ion concentration gives you the pH. So to get a hydronium ion concentration, you just have to take the negative log, do the 10 to that, right? Here's C now. And we know from the last lecture that hydronium ion concentration is equal to 10 to the negative pH, right? 10 to the negative pH, okay? Which you are given a pH right here, thank the Lord, right? So all you have to do is say hydronium ion concentration equals 10 to the negative 1.59, okay? And so the hydronium ion concentration should be, and somebody check my math here, it should be 0.026 molar. I think that's what it should be, okay? And remember, I borrowed someone's calculator and showed you on there how to do 10 to the negative, right? There's a little thing there that says 10 to the x, right? You can hit the 10 to the x button, and then just put in negative 1.59 on your calculator, okay? Anybody got a number? You got the same number? Good. Anybody else? All right, so knowing that now, we can actually fill in our ice table. Okay, so here's our ice table. I like how Dr. Pelfrey said, oh, talking about acid-base equilibrium is like ripping the Band-Aid off. But it's more like a slow unwrapping of a suture because it's not very fast, you know? It's not very fast at all. Oh, most of you weren't in here when he said that because he's also teaching acid-base equilibria to his doctorates of nurse anesthesia class right now. And they've been avoiding doing the ice table. So here's our ice table. Okay, so this is the part where Miss Dickens got confused on Monday, right? And the reason why she got confused is because I wrote up here we have H3PO3, right? And it can go back and forth. And then what you end up on that side, and normally, right, if you were doing a normal, just single proton equation, right, single proton equation, it would be this stuff over here on the right-hand side. But it's not, because in the problem, I asked you to only do one Ka, Ka1, right? Not Ka2, not Ka3. So when I say only do one Ka, it means I only want you to remove one proton, right? That one right there. And you're going to ask me, I know someone's going to ask me, how do you know which proton, right? Well, it has to be an acidic proton, number one, right? But number two, both of these are going to be equivalent protons until one gets lost. So it could be either one could be the Ka1, right? So let's just say this top one is the Ka1, and this bottom one here is the Ka2. I only want you to figure out what the Ka1 is. Only one proton, because it'd be a lot more complicated if I asked you to do two protons. There'd be two ice tables, right? So on the ice table then, we'll draw a line down like that. And then, so what we get then over here is H3O plus, right? And then the conjugate base, which is H2PO3, right? Minus. You see how that's different from what's up here? Because up here, it's HPO3, right? In the completed equation, what is it? H HPO3, right? There's only one proton in the completed equation, correct? Right? Right here? In sodium phosphorus, right here, hydrophosphorus, there's only one proton there, right? But down here, what do you have? You've got two protons. The reason why is because I only want you to remove one proton, okay? You could remove both, but you have to do two ice tables and make this problem much more longer than it needs to be. I will ask you another question like this on an exam that's going to have more than one proton, right? So make sure when you're figuring out what the conjugate base is, if I'm telling you to remove one proton, just Ka1, that you only remove one proton, okay, when you write out the equation. All right, so luckily for us, we've already gone through and done a lot of this math, right, in this ice table. Over here, the first one is the initial of the initial of the phosphorus acid. And so we got that right here. We calculated it right there. That's 0.0476, right? Or 475. Close enough. And then we know that in the initial for the hydronium ion, before any equilibrium occurs, it's 0 and it's 0, right? The other thing that we've already done using all the math, which is great, is that we have gone through and figured out that the hydronium ion concentration, right, is 0.026 right there. That's great because now we can fill that in. We know that the the phosphorus acid lost this much, and then the hydronium ion gained this much. And then we know for every one hydronium ion mole, there's the same number of moles of what? The conjugate base. So that's also going to be a plus 0.026 over there, right? Good stuff, good stuff. So this is something you should probably write down. When someone gives you the pH, like me, the pH will actually give you the hydronium ion concentration, which is actually the what? The equilibrium concentration. So all we have to do now is do the arithmetic, right? Make sure that everything's clear up there. Looks good. We just have to do the arithmetic. This minus this is what? It's going to be 0.022. And then, like I was just saying, put a big star next to this. I gave you the pH. The pH is going to be the equilibrium concentration, okay? You don't even have to draw it out the ice table to know that. If I give you a pH, that's going to be the equilibrium concentration for hydronium. So the answer here is 0.026, and the number here is also going to be 0.026. Okay? And we know that the hydrophosphorus ion here is the same as the hydronium ion, because for every one hydronium that's made, also one hydrophosphorus is made, right? All right, last step. Oh, well, we're not even done yet. Okay, so all that is done right there, okay? So we're still looking for the Ka, right? Oh, wait, we're looking for the percent ionization first, and then the Ka. So if you remember from the previous slide, a couple of previous slides ago, percent ionization, ion, there, percent ion equals the concentration of hydronium at equilibrium divided by the concentration of the original acid times 100%, right? Okay. And so all we need to do there is get our hydronium ion concentration, which we found out from the pH, right? Which is here. So that's 0.026 divided by the concentration of the acid, which is we found out here, 0.0476 times 100. And what does that equal? I calculated it to be 55%. Now we'll figure out what Ka is. What is Ka1? And if you recall from the equation, the expression I gave you before, K1 equals exactly the same as it always equals for every single equilibrium thing. It's products divided by what? Reactants. So this is another reason why I had it as H2PO3, because it's going to be H3O plus times H2PO3 minus all over H3PO3, right? I did this math already, and I ran out of room here, so I'm just going to have to squeeze it in. It should be 0.026 times 0.026, all divided by what? What should it be divided by? What? No. Yes, exactly. The equilibrium number from the original. Good job, Stephanie. Divided by 0.022. Because remember, when you get it down to this equation right here, this is called the equilibrium expression right here. The Ka is called the equilibrium expression. So the only numbers that should be going in here are what? The numbers from the equilibrium line of the ice table, right? Does that make sense? Right? Equilibrium expression, numbers only from the equilibrium line. I mean, the only reason why we make an ice table is to get to these numbers down here. That makes sense? Right? I know, this is a long problem. Yes, that is correct. Or you can just make it easy on yourself and say equals 0.031. I don't usually use scientific notation unless it's like to the -7 or something, right? Something that has a crap ton of zeros I don't want to count. But if it's only got a couple zeros, I'm okay with writing it out in what we call float decimal point. Okay? And then so that actually ends all of C. And then the last one, D, it says how does the osmotic pressure of 0.05 molar solution of HCl compare qualitatively, not with numbers, but qualitatively to 0.05 molar solution of sodium, I mean, not sodium, phosphorus acid, right? And if you remember back from the solution equilibria, solution properties lecture, osmotic pressure is all about how many particles that you have in solution that are actually dissolved in the water, right? And we found out from here that the percent ionization of the phosphorus acid, right? Phosphorus acid, which is hard to say sometimes, uh, is only 55%. Okay, so only 55% of the phosphorus acid actually dissolves into the water and becomes particles in the water, right? But what did I say about hydrochloric acid? What kind of acid is hydrochloric acid? So phosphorus acid is a weak acid, right? So it only ionizes 55%. Yes, hydrochloric acid is a strong acid. It ionizes 100% of the time, right? Which means that the osmotic pressure of hydrochloric acid is going to be way higher than the osmotic pressure of phosphorus acid, right? Does that make sense? Because the more protons you have in solution, right, that are actually dissolved in the water, the higher the osmotic pressure. And in this case, for hydrochloric acid, right, in this case for hydrochloric acid, it's going to be 100% versus 100% versus the 55% there. Okay. All right. Any questions on this problem before we move forward? Because osmotic pressure is about having the amount of particles in the solution. Okay. And so, what is hydrochloric acid compared to phosphorus acid? It's very strong, which means how much of it will ionize? Pretty much, right? And so if all of the hydrochloric acid is going to ionize, that means it has way more protons in solution than, exactly, way more than the phosphorus acid. And so that's why it's going to have higher osmotic pressure, 55% to the 100%, right, of hydrochloric acid.